Hello and welcome to this clip going through some basic ideas to do with haloalkanes. We'll start by having a look at what they are and how they're named, before moving on to a little bit about their shape and bond angle, before finishing off by looking at how we make them and a bit about their reactivity. So basically they are similar to alkanes, but you have one or more of the hydrogen atoms replaced by halogen. So for example, trichloromethane has 3 chlorines replacing 3 of the 4 hydrogens around that carbon. You can get more complicated examples where you get multiple substitutions of more than one halogen. When you do that, you need to be a bit careful about the naming, looking closely at the alphabetical order, so C comes before F, chloral before fluoro, and making sure the locant numbers are as low as possible. So some haloalkanes are quite useful. Many are valuable intermediates in organic synthetic pathways in the production of other molecules. So a prefix is added to the name of the alkane depending on what halogens are attached. So you can get fluoro, chloro, bromo, or iodo, for example. And we also look at the number of halogen atoms that are attached. And that means a prefix can be put in place before that as well. So we can have difluoro or tetrabromo, for example. We also put locant numbers in, that I've mentioned already. That indicates to the reader which carbon atoms in the molecule each halogen is attached to. So the shape and bond angle in the haloalkane is the same as you'd find in a normal alkane, in other words 109.5 degrees and tetrahedral shape. So we make them in several ways. One way is radical substitution, and another way is by electrophilic addition. So with electrophilic addition, if you use just a hydrogen halide, you get a monosubstituted product, in other words, a haloalkane with one halogen attached. And if you use a halogen molecule, because the halogen molecule is diatomic, you get a dihaloalkane. The problem with radical substitution is you get further substitutions taking place that are a bit out of your control. So this means it's quite an inefficient method for making haloalkanes. So sometimes what we do is we use substitution of halogen onto an alcohol molecule. So the first thing to do is to create a halide ion by reacting sodium halide salt with concentrated sulfuric acid in the influence of heat, and that produces sodium hydrogen sulfate and the hydrogen halide in aqueous solution. And from that aqueous solution you can get the halide ion. So the halide ion can then substitute for the OH group in the alcohol and make a haloalkane for you. So the carbon-halogen bond in your haloalkane is polar, which means that the more electronegative halogen draws the electron density in the carbon-halogen bond towards itself. So this makes it susceptible to attack by nucleophiles. A nucleophile is a species that has a lone pair on it, and the lone pair means that it can form a dative covalent bond. It can be a charged species, like an ion, halide ion, for example, or it can be a molecule that's neutral. These are just some examples. So haloalkanes react by nucleophilic substitution, so let's look at the OH- ion, hydroxide ion, as a nucleophile. The nucleophile attacks the back of the carbon atom, in this case because the hydroxide ion is charged, so therefore, because it's negatively charged, it'll be slightly repelled by the delta negative chlorine. So it moves around the back of the carbon in order to react with it. This mechanism isn't quite right because you have the OH- moving towards the carbon to which the iodine is attached to, but in the proximity of the iodine atom. So a slightly corrected version is at the bottom, showing that the OH- moves around the back. So finally, the reactivity is determined by the bond enthalpy of the carbon-halogen bond, which, as you can see, is lower than the carbon-hydrogen bond. This also means it's more polar, so for both those reasons, the carbon-halogen bond is vulnerable to attack by incoming nucleophiles. So as the size of the halogen atom increases, the carbon-halogen bond becomes weaker because the attraction of the halogen nucleus from the bonded pair gets lower. So that takes us to the end of our short introduction. Thank you for listening. Until next time, see you soon.